All right, we need to have a conversation about the scientific method because this is the thing that holds all science together. It is a process by which science is conducted. And we're going to go over the steps, but I want you to think of these as guidelines. Depending upon the type of research that you're doing, the results of the research that happen, questions that come up during your research, maybe not all of the steps are always done. So these are a little bit more like guidelines rather than actual rules. Your basic steps are you're going to start with making a conjecture, kind of like making a hypothesis or an observation of something that's not understood. I weeded my garden. 2 days later, there are weeds. How did the weeds get there? An observation that you didn't understand. What is the impact of fertilizer A versus fertilizer B? If you're in a greenhouse, is one fertilizer going to be more cost effective for you? If you're doing a high school science fair, sometimes I've seen these ones. Do plants grow better with water, milk, or pop? One of the things that I'm looking at is I have kind of made this observation or note that it looks like many younger trees have been planted improperly. So I'm going to do a research project on looking at trees of different sizes and seeing if they've been planted properly. So I made an observation and I made a hypothesis that younger trees are not being planted properly relative to older trees. So that's my hypothesis, that younger trees are not being planted properly more frequently than older trees were. Now we have to test the hypothesis. We have to set up some sort of experiment to see if the observations agree or disagree with our hypothesis. And we want to do this in such a way that we're trying to eliminate errors. Errors such as, I want fertilizer A to do better, therefore I'm going to look for anything that is fertilizer A does better. So we can eliminate some of that by randomizing things. You can have blind trials, which is often what they do in medicine. In a greenhouse, you can space your plants all over the greenhouse so that you are eliminating possible impacts of differences in areas of the greenhouse. This area of the greenhouse gets a little bit more sun, this area is a little cooler, that sort of thing. So we're trying to set up our experiments to eliminate these possible errors. Then the not fun stuff happens. You have to analyze your results, and this is where you're going to be using statistics. You might have photographs, you might create charts, etc., etc. And what you're trying to do is see why things happen that way. Then once you're done with that, now you start comparing what happened to your original hypothesis. It doesn't matter if it agreed or disagreed. What we're trying to do is see what happened with the original hypothesis. Based on that, you might have to make a new hypothesis, generate some new experiments. You might have to repeat the experiment to make sure that you got the results, particularly if you got something unexpected. So if something different happened and you didn't expect that to happen, well, maybe there was a bias there that you didn't anticipate. Some other things. Other people have to be able to replicate and verify your results. You have to be able to perform the same experiment in the same way multiple times over and over and over to say, yes, this is exactly what's happening. This is indeed what's going on. We need peer review. Are there problems with peer review? Yes, of course there are. But it helps to have other scientists looking at your research. Once you go through that, then it's published in a scientific journal. The hypothesis has to be testable. Is fertilizer A or fertilizer B better? Is fertilizer better than no fertilizer? Is potting media better than topsoil? Is topsoil better than garden soil? Those are all things we can test. Modern science produces really, really small changes. We're testing very specific things. And the knowledge accumulates over time, over many, many experiments. And knowledge isn't permanence. And that's a thing that's difficult for some people to understand, that our knowledge can and does change over time. So let me give you a classic example. 500 years ago, everybody knew the world was flat. until we proved that it wasn't. 1,000 years ago, everybody knew that the Earth was the center of the solar system until we proved that it wasn't. So facts and knowledge change all the time. We cannot test moral or ethical issues. We can test this chemical or this drug on humans or animals, but should we test it? We cannot test religious issues. I cannot test your belief in something. And maybe right now we simply lack the equipment. Several hundred years ago, we didn't have the equipment to see cells, and now we do. So maybe ghosts actually exist, but we don't have the equipment to show that they do. We have to think of some of the biases. We have to think of the challenges of uncertainty. So, did this test produce a false positive or a false negative? What are the chances of that happening? Have we done a test long enough to know, often enough times, to know what the chances of a false positive or a false negative are? Is the population large enough to extrapolate to all populations? If I test 10 plants for some growth parameter, is that enough to say that all plants do that? Or even all of that species do that? We also have to keep in mind biological differences. There's always a bell curve when it comes to animal and plant behavior. And so what you're trying to do is, do most of the plants behave this way, or is this little segment of population an outlier in some reason? We really have to come to grips with the fact that science defines terms often very differently than non-scientists define those terms. A very simple example is mass versus weight. Commonly, we throw those words around like they mean the exact same thing, but they actually don't from a science perspective. The big one that everybody always does is theory. When I say I have a theory that this happens, as a scientist, that does not mean what you think it means. We throw the word theory around a lot. We use it like it's a hunch or speculation. But in science, it is a comprehensive explanation that is supported by facts gathered over time. The theory of gravity. Okay, as always, if you have any questions, do not hesitate to contact me.